Isaac Newton stands as one of the most influential figures in scientific history, whose work transformed our understanding of natural phenomena. His groundbreaking studies in physics and mathematics revolutionized thought in the 17th and 18th centuries and laid the foundation for modern experimental methodology. In this discussion, we delve into Newton's contributions across diverse fields, including empirical analyses of heat transfer, fluid dynamics, and precise measurement techniques. Our focus investigates the quantitative relationships in his laws, such as the proportionality inherent in cooling and viscosity, and examines the numerical innovations implemented during his tenure at the Royal Mint. This exploration further dissects his methodological rigor, his insistence on mathematical proofs, and the systematic approach that anticipated contemporary scientific standards. Additionally, we scrutinize his deep involvement in both technical and administrative roles, illustrating how his theoretical insights translated into practical reforms, from refining coinage to enhancing economic regulation. Equipped with technical analysis and complex, data-driven perspectives, this presentation offers a comprehensive review for experts, revealing layers of meaning in Newton's work that extend far beyond basic Newtonian mechanics. Today, the integration of advanced mathematical scrutiny and detailed historical evidence compels us to appreciate Newton's enduring legacy in science and public service. Newton's contributions to scientific innovation extend deep into the technical fabric of physics, revealing profound insights that maintain relevance today. One of his foremost accomplishments is the formulation of the empirical law of cooling, which articulates that the rate at which an object exchanges heat is directly proportional to the difference in temperature between the object and its environment. This relation, though simple in its proportionality constant, has far-reaching implications, as it allows for the quantitative analysis of convective heat transfer. By establishing this foundation, Newton provided an early framework for understanding thermodynamic processes that would later be refined by the principles of energy conservation and statistical mechanics. In parallel, his work on viscosity led to the introduction of what is now known as the concept of a Newtonian fluid. He demonstrated that the shear stress between adjacent layers within a fluid is linearly proportional to the velocity gradient, formalizing this as his law of viscosity. This insight was not only mathematically elegant, but also fundamentally practical, forming the basis for modern fluid dynamics. Engineers and scientists today build upon this understanding to analyze and design systems ranging from microfluidic devices to large-scale aerodynamic structures. Newton's technical prowess is further evidenced by his skillful integration of empirical observation and theoretical modeling. He meticulously recorded experimental data, employing precise measurement techniques that established reproducibility as a critical element in the scientific method. His approach allowed for numerical verification of his theories, thereby bridging the gap between abstract mathematics and tangible physical phenomena. By quantifying relationships through mathematical expressions, Newton propelled a quantitative revolution in science. Newton's empirical methodologies also revolutionized instrument design of his era. His dedication to quantitative precision led him to develop innovative techniques such as refined telescopic observations and calibrated instruments that minimized systematic uncertainties. In an age when measurement errors could obscure discovery, Newton's insistence on accuracy marked a decisive departure from qualitative arguments. His methods not only advanced physics, but also informed emerging fields across engineering and the natural sciences by establishing universal standards for direct measurement and error analysis. These rigorous practices laid the groundwork for modern statistical data evaluation, fostering an enduring legacy that continues to influence experimental protocols and computational modeling in contemporary research. This concise integration of theory with meticulous empirical observation provided a transformative blueprint that has shaped innovations and remains a cornerstone of scientific inquiry. Newton's philosophical contributions to science encapsulate a departure from speculative tradition toward rigorous empirical validation. His famous declaration, hypotheses non fingo, reflects a conviction that theories must be built solely on demonstrable phenomena rather than on conjecture. This principle dictated that all scientific explanations require quantitative support and careful observation, a stance that catalyzed the evolution of methodological rigor across scientific disciplines. Newton argued that absent reliable data, one ought to refrain from positing unsubstantiated mechanisms, thereby aligning theory with observable evidence. Within his seminal work, Principia Mathematica, Newton outlined four guiding rules that have profoundly influenced the scientific method. Firstly, he urged the acceptance of only those causes that are both true and sufficient to explain natural phenomena. Secondly, he maintained that similar effects should be traced back to similar causes under equivalent conditions. Thirdly, he believed that qualities common to all bodies revealed through exhaustive experimentation must be held as universal truths. Finally, he emphasized that hypotheses should remain provisional until disproved by new empirical findings. These axioms not only defined Newton's own research, but also laid the groundwork for experimental science's progression. Newton's systematic approach encompassed extensive experimentation, meticulous record-keeping, and the integration of mathematical analysis to validate observations. His work on the properties of light, for example, was underpinned by a series of rigorous experiments that incrementally built a case for his theories. He reduced complex optical phenomena into measurable elements, allowing for the derivation of precise, reproducible results. This process underscored the importance of reproducibility and verifiability in scientific inquiry and set a benchmark for subsequent empirical research. Moreover, Newton advanced the concept of induction as a method to generalize findings from specific observations, thus establishing a pathway towards theoretical universalism. His insistence on reducing the number of assumptions in explanations was not merely a philosophical preference, but a strategic framework for constructing robust scientific theories. By doing so, he minimized the influence of human bias and speculative reasoning on scientific progress. It is this dedication to rigor and clarity that has cemented Newton as a foundational figure in scientific thought, ensuring that his methodological insights continue to shape contemporary experimental practices and theoretical formulations alike. Newton's philosophical stance not only revolutionized experimental science, but also redefined the role of mathematics as the language of nature. His explicit separation of empirical evidence from speculative hypothesis has influenced countless experiments and theoretical models. By insisting on precise measurement and logical consistency, Newton set a higher standard for scientific communication. His methodological framework challenges modern researchers to maintain clarity and objectivity, ensuring that every model is supported by replicable, quantitative evidence. This legacy continues to inspire rigorous scrutiny in both fundamental and applied sciences, truly enduring legacy. Newton's tenure at the Royal Mint represents a fascinating intersection between scientific intellect and practical economic reform, exemplifying his versatile contributions to society beyond academic inquiry. Appointed in the 1690s, Newton transitioned from scholarly pursuits to a role of considerable administrative and technical responsibility. His appointment came during a period marked by widespread counterfeiting and monetary instability, necessitating both innovative reforms and meticulous technical oversight in coinage production. Newton's approach to the Great Recoinage of 1696 was emblematic of his scientific temperament. He employed quantitative analyses and precise measurement techniques to assess the magnitude of counterfeit coins, estimating that nearly 1/5 of the detained coins were fraudulent. By personally engaging in undercover investigations and cross-examinations, Newton applied his methodical rigor to the realm of financial regulation. His work involved detailed scrutiny of minting processes, where he leveraged his expertise in precision measurement to reduce the standard deviation of coin weights significantly. For instance, he accomplished the challenging improvement of reducing the weight variability of guineas from an average deviation of 1.3 grams to approximately 0.75 grams. This reduction was not merely a technical correction, but a transformative change that enhanced the integrity of British coinage and increased public confidence in the monetary system. Furthermore, Newton introduced the practice of testing a 1-pound sample of coins during the Pix trials, significantly tightening quality control measures. This small change had profound economic implications. It curtailed the margin of error during coin production and saved the treasury an estimated sum equivalent to millions in today's currency. His interventions at the Mint were grounded in his analytical approach, a synthesis of rigorous data collection, statistical analysis, and mathematical modeling that continues to inform modern quality assurance practices in various industries. Newton's economic reforms at the Mint extended beyond immediate technical corrections. His authoritative report in 1717 on the bimetallic exchange between gold and silver triggered a royal proclamation that redefined the legal exchange rate between gold guineas and silver shillings. This decision inadvertently initiated a shift from a silver standard to what would later be recognized as Britain's first gold standard, encapsulating the far-reaching impact of his analytical insights on national economic policy. Although historians debate whether this outcome was a deliberate policy objective or an unintended consequence, the transformation underscores Newton's critical role in reshaping monetary affairs. The technical improvements instituted under Newton's leadership not only streamlined the minting process, but also significantly reduced instances of fraud and counterfeiting. His unwavering commitment to precise calibration of weights and measures established a benchmark for regulatory practices in subsequent periods. Strict enforcement, coupled with innovative quality control measures, transformed the operations of the Mint, ensuring uniformity in coin production and fostering long-term economic stability. In his multifaceted role at the Mint, Newton merged his scientific exactitude with a pragmatic dedication to national economic stability, demonstrating that analytical rigor is equally applicable to monetary policy as it is to natural phenomena. His dual legacy as a pioneering scientist and an adept economic reformer remains a subject of scholarly admiration and continues to inform current practices in both public service and fiscal management. Newton's administrative reforms were supported by his analytical expertise, which ensured that every step of the recoinage process was optimized for efficiency and accuracy. His work model combined methodical surveillance, statistical evaluation, and precise engineering, setting new standards for governmental accountability and financial operations. This comprehensive integration of science into public administration continues to serve as a paradigm for effective economic policy implementation even in modern times. His visionary approach bridged the gap between theoretical research and real-world applications, inspiring reforms through time. Newton's knighthood in 1705 marked a turning point in the recognition of scientific achievement within a traditionally political landscape. Conferred by Queen Anne during a royal visit to Cambridge, the honor was imbued with political nuances rather than being solely an acknowledgement of Newton's monumental scientific contributions. Despite his preference for remaining engaged in scholarly pursuits, his role as president of the Royal Society further solidified his stature among contemporaries. Newton's interactions with eminent figures, such as John Flamsteed, illuminated the competitive environment that characterized the early scientific community. His premature publication of Flamsteed's data in the Historia Coelestis Britannica generated significant discord, underscoring the tensions inherent in intellectual rivalry. Moreover, his acceptance into the French Académie des Sciences testified to his international reputation and the universal respect accorded to his innovations. The knighthood, therefore, not only celebrated Newton's academic and technical prowess, but also symbolized the progressive transformation of scientific inquiry into a status worthy of national honor. This recognition lent significant legitimacy to the emerging field of science, bridging the gap between academic achievement and public recognition. Newton's knighthood set a precedent, inspiring future generations of scientists to pursue excellence with societal impact, an enduring emblem of progress. Despite his towering contributions to science and public service, Newton's personal life reveals a complex interplay of modesty, competitiveness, and introspection. He was known to be reclusive, often preferring deep contemplation to social interaction. Yet historical records indicate that he maintained significant personal relationships with a select group of intellectual peers. His correspondence with figures such as Nicolas Fatio de Duillier and Robert Hooke highlights not only collaborative endeavors but also intense rivalries that occasionally escalated into public disputes. In particular, his contentious exchanges with Hooke reflect a blend of self-deprecation and sharp criticism, encapsulated by his famously ambiguous remark about standing on the shoulders of giants, a statement subject to various interpretations by his contemporaries. Newton's temperament combined an unyielding dedication to empirical truth with a capacity for personal vulnerability. His meticulous nature in scientific inquiry extended to his personal habits, where he was known for his detailed record-keeping and a preference for solitude. Yet he was not entirely isolated. His interactions with students and colleagues revealed a man who valued intellectual challenge and was willing to engage in spirited debate. Moreover, anecdotes from his later life suggest moments of quiet kindness, as well as instances of rapid or irritable behavior during periods of stress, possibly exacerbated by his intense focus on multifaceted projects and his alchemical pursuits. His enduring reputation is that of a man who, despite personal eccentricities, was driven by an insatiable curiosity and an unwavering commitment to uncovering the mysteries of the natural world. Contemporary scholars have debated the intricacies of Newton's personality, noting that his private disposition often contrasted sharply with his public assertiveness. His complex character, marked by both humility and fierce determination, provides insight into the human dimensions underlying revolutionary scientific advancements. He remains a figure of enduring fascination and profound critical introspection. Newton's theological inquiries reveal an intellectual curiosity that extended well beyond the realms of physical science. Despite being born into an Anglican tradition, he pursued a personal study of biblical texts that led him to challenge orthodox dogmas. His private manuscripts, which detailed rigorous analyses of scriptural passages and early church writings, remain a testament to his commitment to exploring religious questions with the same meticulous rigor he applied to natural phenomena. Newton's critiques of the Trinity and his preference for a rational, non-dogmatic interpretation of Scripture suggest that his theological views were as innovative as his scientific theories. Deeply engaged with the early writings of Church Fathers, Newton examined various interpretations of prophecy and textual inconsistencies. His work on the chronology of biblical events and the precise dating of the crucifixion is supported by numerical analyses and historical data, demonstrating his effort to align religious events with observable phenomena. Despite the potential controversy of his anti-Trinitarian views, Newton deliberately kept his theological opinions private during his lifetime, a caution that underscores the sensitive intersection between faith and science in his era. Newton saw divine order as a guiding principle underlying both natural law and human morality. He believed that the same mathematical precision governing celestial mechanics was also reflected in the logical structure of the Bible. His theological studies, marked by an objective and empirical approach, established an early model for critical biblical scholarship. In his later writings, Newton argued that understanding the divine design required an integration of faith with reason, a perspective that continues to influence modern interpretations of the relationship between science and spirituality. Newton's approach to theological inquiry was marked by analytical precision akin to his scientific endeavors. He meticulously examined ancient texts and numerically evaluated prophetic timelines, reflecting an integrated methodology that bridged faith and rational inquiry. His work in this domain remains influential among scholars who study the interplay between religion and science.